Okay, hanging in there last talk before lunch. So for those who diligently check your schedule, you'll see that I took the liberty of changing my title, not because I completely changed what I want to talk about, but in the discussions and presentations yesterday, I thought I want to sneak in one more line of work that might catch maybe your attention. So let me begin with a video that I always look at, and I don't get tired of it because it just shows what human movements, what human actors can do in absolute perfection. And surely she is flexible and has strength, but she also has the utmost elegance. And that is the first thing, just to mention that elegance is partly seen in the trajectories of the endpoint. The second thing that is particularly admirable in her performance is how she interacts with objects of all kinds of complexity, including objects that have infinitely many degrees of freedom. So, how can humans control such complex movements? And let me first take a very high-level view on this before I home into some of the symposium topics. So we know that the neuromuscular system is high-dimensional, nonlinear, with many different spatiotemporal scales, and with a slow transmission speed and noise and variability everywhere. So how on earth is this impossible system able to perform movements as we just saw? In particular, when we look at the numbers here, and compared to robots, humans have a dimensionality of 200 joint degrees of freedom and 600 muscles, whilst the best robots so far are sort of up to 50 degrees of freedom. Our actuators are not very precise, bandwidths 10 hertz compared to 100 hertz and more in robots. Transmission speed is awfully slow. It's 100 meters per second, again, compared to something that's much faster in robots, and the feedback loop and the delays that we have to cope with is a minimum of 100 milliseconds, 200, 300, and so on. And there is noise at all levels. Now, with all respect to Janet's robots, I would say, why do robots still not as well as humans do? With all respect to your robot. So the answer that I would like to give is that humans develop subsystems in this very complex machinery that they have, subsystems that have stability and thereby relative autonomy from central control, right? We walk and talk, so something is relatively autonomous. What are these subsystems? And again, let me give that very high-level overview, and that is what I would like to say dynamic primitives, but in the context of the symposium, I throw in invariances. So what are these dynamic primitives? Well, they are cyclic, oscillations with limit cycle stability, fixed points, and moving fixed points, trajectory with stability, and then impedances for interactions. So that is a real big picture, and it would be a very tall order to have the one experiment that demonstrates this is it. So what I would like to do is to show you some pieces of our experimental studies that are consistent with some of these ideas, and in particular, I will show a couple of studies that focus on the contribution of oscillations in our movement system, and then at the end more with respect to trajectories. So let me go over that. In fact, there's a lot of evidence already, and I want to show you some. Let me begin with an observation on actions, unconstrained actions in space, such that we look how geometric features arise between the endpoint and joint space. Now, the observation goes back as far as 1984, and it has been labeled the two-thirds power law, which is a relation between the geometric and the kinematic aspects specific in trajectories, specifically identified in cursive handwriting. And here is one example of a cursive letter A, that when you look at the curvature over time and the angular velocity over time, then you see that there is a correspondence, a correlation, such that peaks in the one trace correspond to peaks in the other trace, such that angular velocity is a function of the radius of curvature, velocity. And there is a so-called velocity gain factor that then changes across segments because, of course, we don't have continuous curvature, not continuous, constant curvature that changes. So moving on with some old data out of these 1980s papers, just again to show that when tracing out irregular curvatures like this on the plane, typically done on plates so that it's handwriting, you can see that the angular velocity changes in segments. So here, angle over time, there is a constant angular velocity, and then it changes over the course of tracing such an asymmetrical ellipse, asymmetrical shape. And when you plot curvature and angle in log coordinates, you start to see that there is a linear relationship, and that line, those fitted lines, have a slope which is constant, and for shapes like this, the slope tends to be close to 2/3. One more piece out of the old literature here as a elliptic trace that gets smaller and smaller. When you then plot the angular velocity over curvature here in log coordinates, the trajectory traces out these close to linear linear lines, yes, where with every circle the slope gets a little different, and the change in the slope has been interpreted as an indicator when we produce segments in tracing out regular and irregular shapes. Okay, where does this come from? Is it represented in the central nervous system? Is it maybe a matter of smoothness? Is it maybe an epiphenomenon of yet other parts of our body? So we started in the late 90s with the following observation. Namely, when you plot two sinusoids against each other, phase shifted, different or same amplitudes, then you get an ellipse, and when you trace that out over time, then that dot moving around here actually exactly produces the 2/3 power law. Now here is a small simulation which hasn't quite survived changes in software since then. But what you see here is that this point doesn't go around with constant velocity, but rather one where the velocity is slower at higher curvatures and faster at straighter parts of this ellipse. It's very intuitive, but it's amazingly robust in human data. So, given that observation of that two sinusoids, two oscillations in this arrangement produces this power law, we hypothesized that maybe oscillations in the joint motions might be responsible for observing this power law at the end point. So, these are just spelling it out how in the Lissajous plot we get this. But stay with me here. We all know joint space into endpoint gives us this relation. And if we have the endpoint trace out ellipses such that we have this expression and we then plug them into this joint to end space relation, then it's not very complicated, but it's also not very nice, such that they're nested sinusoids, and they become kind of nasty at the end when the amplitude of those joint oscillations become big. So what we then thought and argued was that maybe that power law that we observe in these small movements with small joint amplitudes is really very similarly produced as this Lissajous plot, such that oscillations are basically stacked onto each other. When the amplitude gets bigger, then there's nonlinearities coming in, and that power law should no longer be as clean and straight 2/3. So if it is sinusoids or oscillations that produce the power law, then larger amplitudes will increase the nonlinearities. This should lead to a violation of the power law. So what we then did was we had humans draw ellipses, but not like everybody else, small scribbles on paper, but we actually asked them to produce ellipses of various sizes involving all the joints so that we manipulated indirectly the amplitude of the contributing joints. So here is just 3 different such ellipses, which are not accurate, but nevertheless, it's here in the frontal plane, 3 different ellipses. And here is the powers that we extracted. So the power typically is 2/3, but then if you use radius of curvature and tangential velocity is equivalent to 1/3 here. And so plotting this extracted power law here versus the perimeter of the ellipse, 0.33 is that black line. And you can see that indeed for very small ellipses, it is very close to that 1/3, and it gradually deviates from it with a higher confidence band, meaning more variability the larger the ellipse is. And this is 2 meters, so we had big ellipses. Okay, the next thing is we did that same continuous mapping of tangential velocity against radius of curvature, raised to the power 1/3, and then we get this continuous velocity gain factor k for the small, medium, and large ellipses. And then you can see that there is this splitting occurring that is 2 different velocity gain factors that have been interpreted as 2 different segments. All right, what is the different segment in a continuous ellipse? So I would say that was a little warning signal, and so what we then did also was to look at the joint angles, and as we heard already, we have neglecting the degrees of freedom of the hand, we have 7 degrees of freedom in the arm. So here is the 7 traces that we extracted from our joint degrees of freedom, and they are reasonably sinusoidal, except the small joint angles that were not as much involved. So the next step was that, well, firstly, the joint angles were continuously periodic, so where should that segmentation come from? And we would say that this is an artifact, as we demonstrate subsequently. So what we did from these human data is we fitted those joint angles with sinusoids and then averaged over all subjects, extracted amplitudes and phase relations, and then took it onto a robot arm. We had at the time access to a 7 degree of freedom robot arm where we implemented, using inverse dynamics for torque control in the 7 degrees of freedom, to basically replicate an average subject with the fitted sinusoids. And then we measured, just as we did with human subjects, using 3D motion capture, we measured the ellipses that the robot then performed. Human data, you just saw those, and these are the robot data. And here is, again, the same plot from before, and here is the robot data, the power extracted from the endpoint trace. So the robot replicated the elliptic patterns, including the distortions, with completely continuous control in joint space. There was no segmentation anywhere in sight. Okay, and I should say the following, the same thing here, that so-called indicator of segmentation was also replicated, and as we interpreted, was merely due to the kinematic arrangement of the joint degrees of freedom. So in the bigger picture, how I want to also read this now is that oscillations approximated by sinusoids in joint space seem to be an important component for such free drawing movements that then ultimately actually lead to these rather intriguing geometric features in endpoint space. Mind you, it is intriguing not only to us, but it has been intriguing to many others, and there is lots of other work out there that has looked at it as a function of, or can be reproduced by the cost of minimizing smoothness, maximizing smoothness. There has been work that has found correlations in motor cortical activity corresponding to the power law. And Tamar Flash has looked at it in terms of affine geometry and has shown and continued with that actually this power law in extrinsic space corresponds to constant affine velocity. So this observation is packed with interpretations, and I would say none of them are totally contradictory, but maybe different views on the same thing.
The fact that the velocity is proportional to the curvature, or to the curvature of some exponent, means that there is a hidden time scale and a hidden length scale.
Okay.
Right? Because velocity is one dimension.
Yes.
And so what are those? Meaning, if I now try to connect it to the body, what are those length and time scales, and how do they vary depending on what you do or person, or is that something that is known? Should be, but
You're the first to ask this question, and I'm.
okay.
Maybe it's related to the time scale where it breaks down from the power law.
And when you say time scale,
Scale where it breaks down.
No, but there's a hidden scale already, right?
Yeah, so that's where it breaks down. So it should break down beyond that scale.
I don't know.
I'm looking at Ben because he also worked on the power law.
Well, I think here what makes it break down is when the angles
Are
become
small.
big enough. Here, if you can approximate the sinusoid, well, sine of theta as just linear function of just theta, and then you will get very nice linear line. But as the angle becomes big enough, then yeah, you have lots of nested sinusoid. So yeah, it doesn't have to do with any length scale necessarily.
Maybe we'll try again
Okay.
afterwards.
Okay.
Yeah.
So basically, whenever you have to curve, whenever you have a spatial change, you have to go slower. So
Yes.
your mental effort should go into following that trajectory, and whenever it's straight, you can speed up.
Yes.
Basically.
Yes. It's very intuitive. It's just what is astonishing is the systematic nature of this relation. So this was pretty old work already 20 years ago, which together with Stefan Schaaf. And more recently, we took this into the context of human-robot interaction. And we programmed a very simple robot to trace out ellipses in the horizontal plane. And that robot was either doing constant velocity, constant angular velocity, or we programmed it to observe that human-compatible power law, or we made it deviate slightly or really exaggeratedly. So constant velocity would be this. This would be the biological pattern, and this would be an exaggerated biological pattern, really going fast and really going slow, and here's the inverse. What we saw when subjects were instructed to just follow that robot arm was that the forces that were exerted against the manipulandum were highest in the non-biological pattern and lowest in that power law biological pattern. And here is over time, and then here graphically with the force vectors displayed. This 1/3 is the biological one, and the forces are overall smaller than in those other velocity curvature relations. We also looked whether subjects could learn other curvature velocity relations, and using 1, which is that minus eta minus 1/3, so overall subjects did not change even though they practiced this for 1.5 hours. So there's something rather a strong preference in our movements in terms of this curvature velocity relationship. So moving on to something which is seemingly totally different, but there is a commonality in there. Now, as I said, this first part was looking at actions, that is, at looking at endpoint in relation to trajectories in joint space. Now I'm moving out and look at some interesting geometric features in the relation between endpoint to a target in the environment. And the kind of task setting where I look at that is one of throwing. Throwing, in this case, a ball attached to a vertical post, and the person is meant to throw this pendulum around the post to hit a skittle on the other side of the post. So in our lab, we modeled this in a yet simpler fashion, such that you could see it's turned around, you see it from top down, and in the horizontal plane, the post now is like an obstacle, and we have one target, and then the subject is meant to hit that target. So the model that we then use for our virtual implementation looks as such that the red disk is that top-down version of the pendulum pole, and the ball in yellow is suspended by 2 orthogonal springs, such that when you then displace the ball, like the pendulum, to here, and then there's a paddle, which is how our subjects then throw the ball. If you throw the ball at a particular location or angular orientation of the paddle with a given velocity, then the ball traverses an ellipse, yet again an ellipse, and it hits or doesn't hit the target, such that the error is quantified by the minimum distance between the ball trajectory and the target, and the trajectory, one more time, is determined by the angular position of the paddle and the velocity at release. 2 variables that determine the ball path, 1 variable for the result. As I'll expand in a little bit, there is a redundancy of 2 to 1, simplest form of redundancy, that actually opens some very interesting questions and results. But let me first stick, and here's the equations for the ball trajectory and the solution manifold, which is the manifold of 0 error solutions expressed only in implicit form here. So in our virtual experiment, subjects stand and have their arm located on a vertical post, and they can perform a horizontal rotation in the elbow. They hold a ball attached to the end of the manipulandum with a force sensor on it, such that when they move the arm and open the hand, such as in throwing, then they release the force from the force sensor on the ball, and that is online measured. and the angular position and velocity at that moment is taken to calculate the trajectory of the ball in the virtual space. So in one first experiment, I want to first go back to my attraction to oscillations, because as much as this subject tries to knock down a skittle on the other side once, and then again, and again, what we observe is that subjects invariably, without intending to do so, fall into a rhythm. And I'll show you how strong that tendency to fall into a rhythm actually is. So on day one, our subjects do 240 trials. Here, this line is the angular trajectory of the arm, and the dot is when they release the ball and reset, throw, and reset. The only instruction is to hit that target, that skittle on the other side. The pink lines denote the time where they stop. Dwell time, we call it. On day 11, the dwell time virtually disappeared, and visually, I think you trust me that they become more rhythmic, more periodic. So let's quantify that, and surely their error goes down, no big deal. The dwell time goes down, the number of pauses, this is the summed dwell time, and this is just the number of pauses, slightly goes down. This here is a variability of the interthrow interval, and this goes down very fast and then plateaus at about 5%. So they develop a periodicity with a variability of 5% around their chosen period. 5% is what is the variability when you tap, synchronize with a metronome, voluntarily, with a given rhythm. Here, all they want to do is to knock down that skittle, and they fall into this very, very regular rhythm without even knowing it. Now, as I alluded to in the beginning, subsystems with stability, oscillators, these were all kind of high-level keywords that I was flaunting with. So, having observed this emergence of an oscillation, the question was, is there limit cycle stability? Can we estimate whether subjects actually develop a stable rhythm? So what we did here is we plotted that arm trajectory in state space, which obviously then goes round. We did a Poincaré section and took two measures out of this, which is on the one is the projection onto the Poincaré section measured in terms of the standard deviations of the intersections on that, the intersections of the arm trajectory on that Poincaré section. And the second one is the Floki multiplier, which is plotted here. So the standard deviations on this Poincaré map go down, meaning what this is visualized here on day 1 to day 11, that orbit becomes tighter and tighter. The Floki multipliers, which are a measure of stability, they are between 0 and 1, however, they don't change. We were disappointed because we wanted to have some quantification saying that our subjects develop more and more dynamic stability. However, different subjects actually were relatively stable, stable in the sense of didn't change very much over days, but they were very different. So what we did then was to plot the values that individual subjects had to the error to see whether these estimates of stability correlated with the performance error. And they did. To understand this graph here, these are the 11 practice days, and here is the error and the standard deviation on the Poincare map. Each point here is a subject, meaning this subject up here on day 1 had an error, high error, and high variability. And so across the 11 subjects, you get this, this regression. And it gets flatter and flatter, but the slope and the regression is significant through each of the days, meaning those subjects who had less variability also performed better. So in my interpretation, this would mean, and I take a little bit of liberty here, that if you establish this stable rhythm, then stability is resistant to noise, that actually then translates into more reliable releases with better performance. I'm stretching it a little bit, so don't fault me for that. Now, one more piece that nicely supports this data, these results, is we had a second experiment where we instructed subjects to stop and wait for the verbal cue. So throw and then go, the experimenter would say go, with random intervals between each throw. So we actively broke the tendency for subjects to fall into a rhythm. This is success rate and performance error, and the self-paced rhythmic group had higher success rate, and the performance error was significantly lower than the group where we, via verbal cues, broke that continuity and periodicity. Okay, one more. Now, pointing to the redundancy in that task, which is actually surprisingly, call it complex or intriguing. So to say what I already said before, depending on the angle of the paddle and the velocity at release, there are the elliptic ball trajectories that either hit or don't hit the target. And in this top-down view, I show you two examples where the green and the red trajectory go straight through the error, whilst the blue dashed one does not. Those two obviously demonstrate that you can hit the target with zero error with more than one solution, in fact, with an infinite number of solutions. And this is illustrated here, where we plot all the feasible release angles versus the feasible release velocities, and the color indicates the error of the ball trajectory to the target, and this black set of points is the solution manifold, namely that set of points that can achieve zero error for a given target location. Those 2 points just take the release parameters from those green and the red ones into this figure, and the blue one corresponds to here. Okay, next, you can also interpret or use this release angle and release velocity basically as state space of your arm trajectory. So against this depiction of the solution space, we can also just plot the arm trajectories into that same space where, well, of course, for the blue trajectory, you need to release the ball when you intersect the solution manifold, the manifold that achieves zero error, right? And for that blue trajectory, we have exactly 2 points. For the green trajectory, we have more than that, because that is a smart solution. When the subject learns a trajectory that kind of travels sufficiently close to the manifold, then the subject actually creates a window within which you can release the ball without being penalized with an error. So, of course, this is the smart solutions, and what we'll investigate is whether subjects discover that, because this is then a trajectory that is noise resistant or robust with respect to errors and intrinsic noise. How do we quantify that? First of all, we convert, say, this trajectory into what we call an error trajectory. Namely, we calculate or we estimate the target error at every moment of that trajectory, assuming a ball release at every moment, and then plot it over time, like here, and this is the error over time, and then we can compute the timing error, which is when was the actual release to a release here that would correspond to the intersection of the arm trajectory with the solution manifold. So we get a timing error and a timing window, which is basically estimating the time for which the trajectory would achieve ball releases with a subthreshold error. Okay, so now comes the geometry here again, and that is when you place the target at different locations in that workspace, you can create very different manifolds. They're now called in green, and green means very low error, and yellow means a just about touch of the ball at the target. So just by placing the target in different location of the manifold, you create, of the workspace, you create very different solution manifolds. So we took those 4 different scenarios and tested subjects to see whether, regardless of the target placement, they would discover a solution where their trajectory basically hugged along the solution manifold. And here is just a sample of those trajectories. And here is the summary of it. In what we call the U-shape manifold, this data look as follows. Here, over 6 days of practice, we plot in green the error, which obviously goes down, and the success rate goes up. Here is our timing measures and the timing window and the timing error in blue. And you see that this timing error goes down and then sort of hits a bottom around 30 milliseconds, while the timing window keeps climbing. In the J shape, which is the second manifold, well, this is obvious here, but the timing error again goes down and then seems to hit a plateau whilst the timing window keeps going. And what we call box shape, we see a very similar pattern again. Timing error plateaus, and here timing window, well, it plateaus as well. And this is actually control where you shouldn't see anything, which is actually the case. So what we conclude is that, well, firstly, humans' timing precision is approximately 25 milliseconds and above. That is pretty miserable. However, they learn an interesting solution, which is they shape their arm trajectory to create a buffer, a tolerance window, such that their intrinsic noise doesn't immediately affect the result, that is the target error. All right, final 2 slides, just to say that what I showed you was for a fixed location of the subject, and I only moved around the targets. But what I'm sort of trying to portray is that when we perform such tasks with respect to some location in extrinsic space, there is a geometry in the task solution that arises. And of course, we in real life are not fixed in position, but we position ourselves towards the target such that we probably enhance the chances to discover these solutions. And so I haven't looked at that yet, but all I wanted to show here is simulations where for a given target location, we just move the location of the paddle around just from here to there, and here are the solution manifolds as they change as a function of the pivot location. And one more. If we take a target location all the way up here, actually the changes in the manifold are a lot more dramatic. And the question is, which of those would the subject choose? Would they choose one where their arm trajectory then maximizes the time that they are close to the manifold? Okay, so summary. So I showed you in this first study on the power law, I wanted to show you that there is interesting relations between joint space and endpoint space coordinates, in particular that power law, and I was trying to advocate that one of the preferences of humans is to move rhythmically, and that is part and parcel of generating that interesting geometric feature that many people have studied. And in the second study on the strolling game, I wanted to show how, again, interesting geometries occur between endpoint and a point out in the world, and how subjects, I guess, learn solutions defined in this relation and shape their actions accordingly. Okay? And that's us. That's all the workers.
When you showed us these trajectories of velocity as a function of angle, where you had error distributions or noise distributions, that was not uniform. So somewhere it was wider, somewhere it was narrower. Do you see a sense of how individuals exploit that? So some regions are more susceptible to noise in the trajectory, other regions are less susceptible, if I understood correctly.
So let me just try and make sure. You mean this one?
Either that or 2 slides down, 35, either one of them.
So this is no data yet.
Oh, this is the, okay,
This is
the
only
chapter. Okay, thank you.
simulations
Okay.
to demonstrate how.
But even over here, you can actually see that the error is not uniform, right?
Oh, yeah. So in these are all produced numerically, assuming releases with all these different combinations. And I think what this one shows probably best is that the manifold has an asymmetric neighborhood.
Yeah. And so do people, so this is a calculation, but you also have real data. Do people respond differently and focus on different parts?
Yes, this is
during the time of their task.
This is the time. I haven't looked at it in terms of time of the task. I only looked at in a different study where we only looked at the releases in terms of the distributions in this space. And the distributions very nicely find what we call the error-tolerant areas versus, say, this is not the best of depiction, but they would go into the shallower regions.
Maybe a different way of continuing that, if I might, is to ask whether people learn sloppiness when they can and learn accuracy, and then they're forced to be accurate and forced to be sloppy.
Yes, so they learn specifically in the distributions. I have distributions of points. I have made the case in several publications how they find those solutions where they can be sloppy. So yes, I have a follow-up study not yet published where we added noise, and there we showed how the precision of release gets better. So when under pressure, via adding noise, they can still get better. If that is not there, they seek those solutions where they can be sloppy.
Thank you.
Maybe a request for two clarifications. One is how does the periodicity between throws improves error, right? And then the second one, you think that this Floquet multiplier, you think it's a constant for a given person and they just can't reduce it?
Yeah, so so the question is how and why do they become better in the task error when their periodic or rhythmic trajectory becomes less variable? So the short answer is I don't know, other than that the correlations show that it goes together. And let me just maybe add, not your question, but let me add to that I remain to be puzzled that those subjects, or that people when they perform an error, an accuracy requiring task, that they become better when they move continuously versus execute, assess error, correct error, reinitialize. But we have also other data where we see that yet again, that when subjects stay in rhythmic motion, an error or an accuracy requiring task becomes better.
So is it like a top that is stabilized by angular motion? So,
That's my
the motion
interpretation, my
stabilizes
intuition.
noise
Yeah.
and other
So
systems.
just to give you the other example is we're currently looking how to crack a whip, right? This is way too boring. So, so have already collected data of a subject cracking a whip to a target. And in two forms. One, and it was a Guinness record holder, so none of those humble human beings. So he could do it great. Nevertheless, if he did it just as a one-shot task versus keeping the whip in motion, he was better at that latter, at the continuous. Again, it's not, I think I would have intuited the other way around. However, the only way that I can loosely intuit why is because when you stop and initialize, you're at a transient, right? You're at a transient to some end state versus...
A limit cycle or something.
Exactly.
You asked me a question about a deficit yesterday. Let me
Yeah.
ask you one too.
Okay.
In this type of impairment called optic ataxia, an individual, say, when it's fixating a central point, is trying to reach to a target in the periphery, tends to not reach far enough. Okay, and so it's as if there's some lesser gain than there should be. And this doesn't seem to improve with practice. Can we get any insight into thinking about what might be going on here from the types of perspectives you're talking about? I know this is a little bit off the track of what you're talking about, but I'm curious for personal reasons, my own research here.
Well, so as much as I am a great believer in interactive perception and action, I'm still in the boat of every motor control researcher that perception is a stepchild in our thinking. So in that sense, the other sort of loose snippet to your question is that sort of dysmetria is regarded a feature of cerebellar ataxia, so a motor deficit as opposed to an optic deficit. but I'm not familiar with the specific case.
Okay, well,
that
this
you're-
type of deficit is at least interpreted not to be a perceptual deficit. It's not that they don't know where the target is, nor is it a pure motor deficit. It's interpreted as some deficit in visual and motor control, and so, okay,
Yeah,
Thanks.
yeah, so,
no problem.
So it's the rhythmic control is an interesting idea. But then I think I just want to mention the earlier thing you mentioned about the decided pattern and this two-third power law.
Yeah.
So I think it's a nice coincidence. However, it doesn't quite work for other patterns and ellipse drawing. So for example, so if you're drawing, for example, if you draw ellipse with different size, or or doing a spiral, then you should predict a zero power law.
I
According
know
to
your
that.
work, I know your work.
Yeah,
Which is
so,
totally nice, and
Uh-huh.
I wasn't meaning to say that this is the one and only.
Right,
However,
right.
what I've been thinking with respect to your work, which has nicely mathematically shown that when you go into more complex curves, not just the ellipses and the figure eights that everybody has been looking at,
Right.
but clover leaves and other more interesting ones. Upshot is that they remain rhythmic patterns where you trace out.
It
right?
works for any non-rhythmic pattern, any random shape drawing. Yeah.
But I would still hold that in your pattern, as much as I understood, or as far as I understood, that you would still have, repeated, maybe would have periodic or oscillations in joint space in going around, only that it becomes just much more, not much, but more complex beyond that ecision type relation that inspired us. So I just think it's not against it, you just take it one step further into more complex patterns, and you don't see 2/3 or 1/3 anymore, but you still see constant powers, they're just different.
Oh, no, it actually is a whole spectrum of power. So
Yeah,
it's not power
yeah.
anymore in the end. But yeah.
Okay.
Yeah,
I think we need to break for lunch.
There was one more question, we can do that separately.
I think we should break for lunch. We can keep talking over lunch. Thank you. For part of that.